Here we can look back at the history of physics as a discipline, which evolved from something that talked about ordinary objects like planets and cannonballs into something that now is formulated as an information theory that basically talks about information and information processing. In a sense, the boundaries between physics and computing are starting to dissolve. So when we talk about the physical, we're talking about something that can be characterized in terms of some sort of state space.
You may have felt it at a concert or a football game, that moment when hundreds or thousands of people all seem to share a single will. It's a powerful feeling. But what if it wasn't just a feeling? What if being part of a crowd actually had the power to change you into something else? Well, then you might be a locust.
Something that has distinguishable configurations or states. So when we talk about the physical, in a sense, we're making some assumption about how we're going to characterize what can be distinguished. And hence, we're talking about information. What it means to distinguish something is to talk about information. So I tend to think about your question in terms of a division of some universe into two pieces that exchange information by interacting, by physically interacting.
Now, how a solitary grasshopper becomes a swarming locust starts with a change in its environment. The desert locust, one of the most notorious species, is found in arid desert and semi-desert regions from Africa to India. Usually these regions can't support huge numbers of grasshoppers, but when there's more rainfall than normal, the soil stays wetter, more vegetation grows, and conditions become more favorable for the grasshoppers to breed. And that means more baby grasshoppers, called nymphs, hatching together at around the same time. If these nymphs are spread out across the landscape and stay away from each other, they will grow up into grasshoppers. But if they are crowded, they will transform into locusts. There's something about the sight and smell of other grasshoppers that changes their behavior, drawing them together, making them more gregarious, and starting the feedback loop that leads to locusts.
To ask, what does that exchange of information look like? How can we model that exchange of information? How can we model what the systems on both sides of this division that we've stipulated, how can we model what they do with the information? How does each agent or entity act on the other one? A natural way to think about what they do with the information is clearly the theory of computation. They're processing the information in some way. It's very natural to think of this physical interaction, as we would call it, as a communication between two entities who are each receiving information from the other, doing something with it, which we can think of as a decision process or a computational process. And then they're sending a message back.
Locust is what we call these grasshoppers when they are in their swarming phase. When conditions are right, well, it's swarming time. These periodic outbreaks, when they're big enough and include individuals from different breeding areas across a region, are sometimes literally called plagues. The individuals can eat their body weight in vegetation every day, and there can be up to 70 billion of them in a swarm. Once enough of them have started to congregate, they will almost inevitably come into physical contact. These touches seem to increase their serotonin levels, the same neurotransmitter that in us boosts our mood, among other functions. And the touches also produce physical changes. For example, in one study, researchers raised South American locusts in either isolated or crowded conditions. Isolated nymphs were pale greenish or brownish, eventually becoming brighter green as adults. Nymphs that were raised in crowded conditions had orange heads and dark spots on their bodies, and the grasshopper and locust phases of another species called the migratory locust look so different that Linnaeus thought they were two separate species, and it wasn't until 1921 that anyone realized they're actually the same one.
All these ways of talking are formally completely equivalent. So one can bring the language of communication and the language of computing to bear on any physical interaction. This naturally raises the question, if we think of each system as some kind of information processor, how do they structure the input that they receive from the other system? One way to think about that question is to ask, can they detect correlated patterns in the input that they get from the other system?
How can the DNA of a single species produce two totally different outcomes just by being part of a crowd? Well, it has to do with a thing that biologists call phenotypic plasticity. Every locust has its own genotype or set of genetic material, the DNA instruction booklet for making a locust. And every locust, or grasshopper, also has its own phenotype or set of observable traits. How you get from genotype to phenotype depends on how the DNA instructions interact with the environment.
So if we think of this in communication language, can they detect words or sentences or other meaningful subsets in the communications they get from the other system? If we think about it in terms of a sense like vision, we would ask, can they see objects that hold together over time? Being able to detect such structure in the information that they receive, that each receives from the other system, is necessary in order to do any sort of prediction. So when Carl talks about the FEP, it's a least action principle that has to do with minimizing uncertainty about what one's interaction partner will do next.
DNA by itself isn't everything, and potentially having some wiggle room there is generally a good thing. It makes organisms more adaptable to changing conditions. For some traits, the environment can only change the possible outcome a little bit. But in the case of the locust, the environment, crowded or not, matters a lot. We would say that this insect has high phenotypic plasticity and that it is density dependent. It's so extreme that it is even considered a special kind of phenotypic plasticity called phase polyphenism. This means that the two forms, or phases, that these insects can take, grasshopper or locust, are separate and distinct.
Being able to do predictions requires being able to capture some kinds of regularities in the input coming from the other system. So one has to be able to locate parts of that signal that have relatively low entropy. In other words, some sort of relative stability over time. If we pursue this line of thinking, we're very quickly led to viewing what we call ordinary objects, like planets or billiard balls or computers or each other, as constructs, as Carl put it, because they are areas of low entropy in the signals that we're receiving from whatever it is that we're interacting with, that we see only via the messages that it sends to us, or only via the actions that it takes on us. What is often called reality, what we see all around us and hear all around us, is in that sense a construct. It's something that we have to be smart enough to put together using whatever information processing facilities that we have, including, of course, those in our brains. That leads us, of course, almost immediately to ask a different question, which is, lots of the things we see around us look for all the world like other agents rather like us, not just other humans, but all other organisms. And so we can ask, how do they see their world?
As for what drove this adaptation in the first place, it might have to do with ancient changes in climate, at least for one of the genera in the family that includes all the locusts. See, in this genus, the desert locust is the branch of the family tree that split off earliest, probably around 8 million years ago in Africa. According to one study, at that time, the Sahara Desert was becoming more arid as a result of the closing of ancient seaways that had linked the Mediterranean Sea to the Indian Ocean. These also potentially made the African monsoon belt more sensitive to the tilt and wobble of the Earth's orbit, which might have contributed to the edges of the Sahara shifting back and forth. All these things could have made for a less stable environment for the ancestors of the desert locust, which might have selected for individuals who were more adaptable, giving rise to the extreme plasticity we see in locusts today. They could be grasshoppers in the lean times and locusts when there was more vegetation for them to eat.
What is an object for them? How do they view what their environment is doing to them all the time?
And this is both pretty bizarre, and also maybe not that bizarre after all. We've known for decades that DNA isn't destiny. There are all kinds of things that can change the outcome of this so-called blueprint. But it feels just a little more extreme for the locusts, maybe because the trigger seems so simple. It is literally just them bumping into each other that turns them into an entirely different form.
So one is quickly drawn into a kind of ethology, if you will, concerned with how other organisms process what they're getting from their environments.